Welcome to your tutorial for week 5. This week we'll be focusing on multiple regression. Okay, so as you can see here in SPSS, I have 3 quiz scores and a final grade. So today I'm interested in knowing whether the scores on these 3 quizzes predict the final grade in the course. So essentially we want to know if these 3 independent variables have an impact on the dependent variable, which is the final grade. So we can see here that the quizzes are measured in 1 to 10s, and the final grade is on, it looks like 100%, so it's on 100. So essentially we want to know if there is any variance in these quizzes that can explain the variance in the final grade. So to do this, we are going to be calculating a multiple regression, and that is all going to be done through the option Analyze, Regression, and Linear. So once we're in this window here, we do have to begin by checking for our assumptions. So some of the assumptions you would check for just within the data, but you can assume that your data has been cleaned, you have no outliers, and that you have no illegal or impossible values. So what we're going to skip right to is first we're going to check for the independence of the observations. So what we would do here is we would plug in our regression analysis like we would like to run it. So that means that we're going to put our 3 independent variables here and our dependent variable right here. So we'll start with that and then final grade. So we have 3 independents and our dependent, which is final grade. So to get the to test for independence of observations, we have to run the Durbin-Watson test. And actually we can find that right here in statistics. So we'll unselect collinearity diagnostics and instead we'll click on the Durbin-Watson box right here. So we click OK, and that's all we need to do. We click continue and we get our output. So what we're looking for is the value right here. Okay, so we don't need to worry about the model summary and the rest of everything yet. We haven't checked our assumptions, so we actually can't look at that just yet. We just need to confirm this is okay. So we have a value of 2.5, and if you recall, the values will range between 1 and 4, where 2 indicates that we have no issues with independence, whereas if we go closer to 4 or closer to 1, we do have a problem. So as long as it's between 1 and 3, it's okay. Okay, so the next thing we need to check is for whether we have linear relationships in between each of the variables we're looking at. Okay, so what we need to do that is generate a scatter plot matrix. So what it'll do is create a scatter plot for all the different combinations of variables here, and we can just confirm that we see something linear, or at least something that's not linear. Okay, so a blob is okay, but any other pattern, that would be a problem. So to do this, we click on Graphs, Chart Builder, click through this, and so down here we need to check the I'll click reset here. So we want to select in the scatter dot option, we want to select the matrix right here, so we can drag that, close this, and essentially we can drag all the variables we're interested in looking at into this option here. And actually that didn't work. Let's try that again. Oh, it's only taking them one at a time. Alright, so we have quiz 1, quiz 2, 3, and final grade. So from there it's pretty simple. We click OK. And then SPSS is going to generate our variable here, so, or our scatter matrix here. So as we can see, for the most part, things are pretty linear. This one may be a little bit weird, but you know, if we look at it here, it seems okay. The opposite side of it, maybe less so, but it's not non-linear, so we'll go with it. Okay, the rest of them are very obvious, that one here, so just the relationship between quiz 2 and quiz 3 is maybe less so, but for now we can live with it. So, and just in case it's a little confusing how to read this table, it's just like reading a correlation table. So right here, this cell represents quiz 2 and quiz 1, this one is quiz 2 and quiz 3, and this is quiz 2 and final grade. Okay, so we can close that. So we have We can assume that our linearity is okay. So the next thing we have to look for is multicollinearity. So as much as we want to have a linear relationship between our predictor variables and the outcome, we do want to make sure that we don't have too much correlation or too high of a correlation between the independent variables, because it's going to make it impossible to account for which one is causing the variance. So in that case, we would have, if we have two that are perfectly correlated, we would have a redundancy, so we wouldn't want to put both of those variables in the model. So in order to check for this, we have to run a diagnostic test. So this is done in regression linear again. This time though, it's kind of weird. We have to run it based on the number of predictor value or variables you have. That's how many times you have to run this diagnostic. So the first thing you need to do is take out final grade, because we're not interested in whether we have multicollinearity between the independent variable and the dependent variable. We're more concerned about multicollinearity between these variables. So we'll have to run it each time. So once with quiz 1 as the dependent variable, once with quiz 2 as a dependent variable, and then finally a third time with quiz 3 as a dependent variable. So we'll start with quiz 1. So we just take it out, put it back up here, and then we go in statistics, and this time we'll unselect the Durbin-Watson test, and we will select the collinearity diagnostics. So we click OK, that's all we need. And this time in our output, we are looking for the coefficients right here and the table. So we can really just focus on this here. What we're looking for in the tolerance is that it's above a value of 0.2. So 0.99 is way above that, so we have no problem here. And then for the VIF, we want something that's under 10. Okay, so 10 is a very kind of large range. Under 5 is ideal. So in between 5 and 10, there might be a problem, but over 10, there's definitely a problem. But in this case, 1, we're nowhere near that. So right now, we can conclude that there is no multicollinearity between quiz 2 and quiz 1 and quiz 3 and quiz 1. So now we'll redo it with one of the other combinations of variables. So again, regression linear. So this time I'm taking quiz 1 out, put it down here, and now I'll put quiz 2 at the top. We rerun it, and again, as you can see here, we have 0.9s and around 1, so there's no problem with quiz 3 and quiz 2 and quiz 1 and quiz 2. That just leaves us one last one to check, and that's quiz 3. So we do analyze, linear, start by taking quiz 2 out, putting it down here, and then putting quiz 3 up here. We click OK, and so we have a little bit lower of a tolerance here. We're at 0.4, however, it's still not below 0.2, so we have no problem. And we're a little bit higher here as well, but we're not above 5 or 10, so it's not a problem. Okay, so we can assume that we are okay when it comes to multicollinearity. We do not have it, so it's perfect. Okay, the next thing we have to look for is the homoscedasticity of the variance. So what we want to make sure is that the variations in final grades are similar across all the different levels for the quizzes. So to do this, it's pretty easy. We go back again to our same menu, regression linear, and this time we want to put our model back in. Okay, so we've got our 3 quizzes here and our final grade right here. We can unselect the collinearity diagnostics, and we'll go to plots, and this time we're interested in plotting the z-scores of our predicted values, and we want to see how they relate to the residual value, so the difference between the predicted values and the actual obtained values. So what we want to do here is put the standardized predicted, so z predicted, on the x-axis, because it's going to be the bottom part of our chart, and then we want the residuals right here, so the y. And then we click continue and OK. And we can ignore all of this, and we're just going to scroll down to our table here, our chart here. So again, what we're looking for this time is that we want it to be pretty consistent across the entire range of values at the bottom here. So these are of course in standardized scores, but we wouldn't want to see a cluster of scores here and a cluster of scores there, because it would mean that the variance isn't the same across all the different values of the predictor variables for the predicted variable. So in this case, it looks pretty good, but if we double click here, another window is going to open, and we can select this little option here to get a line of best fit. So we can just click, once it's there, we click close, and you notice this line appears. So what this has essentially done is it's added a regression line for this table, and in this case, we want it to be as flat as possible, because that means that there isn't any kind of unusual relationship here. So it's a totally flat line, which is exactly what we would want. If you had something that went like this, it would mean that there is a problem and that there's more variance at one end of the scale, or the predicted variables rather, than the other end. But in this case, it is fine. So we can close, and we are now ready to proceed with our regression analysis. So this time we'll go back, regression, linear. So we again still have our final grade here and our 3 quizzes there. So for the first one, we're going to do a forced entry regression. So this means that we're going to put all of these in at once, and we're going to let SPSS assume that they all can account for variance equally. Like there isn't one that should be considered before the others. They're all going to be considered at the same time. So just ensure here the default is enter, and which is the forced regression option here. However, there's other options there, including stepwise, but you don't need to worry about that for now. So in statistics, we are interested in knowing the estimates. We want to know our model fit, our R-square changed, and that's it for this. The plots, we no longer need this plot, so we can remove that. Okay, we won't be doing anything in saved for now. Options, we can leave it here, and then of course we will select our bootstrapping option in order to ensure that even if we do have any issues with normality or anything, that it's being corrected through the bootstrap. So we're going to get our bootstrapped confidence intervals for each of the parameters we're estimating in our model. So we are ready to run. We click OK, and we get a number of outputs. Okay, so first thing we have here is a summary of the model. So what we can see is that it ran a model with all 3 of the quizzes predicting final grade. Okay, so they were all included, nothing was removed. So the next part here, we have our summary. So we have the R value, which is the correlation of all 3 of these with the dependent variable. The R square, which is our effect size, so how much variance is accounted for, or how much of the variance in the dependent variable, so final grades, is accounted for by the 3 quizzes. We have an adjusted R square, which basically is just a slightly adjusted version that takes into account the fact that we're generalizing our data, and what we want is this to be as close to that as possible. So a 0.02 difference is perfect. So this whole section here, the R change, when you only run one model, it's comparing it to 0. So you'll notice the R squared change is the equivalent of R square because we started at 0, and that the F change, okay, so it's the same as here, starting at 0, and then we have the degrees of freedom and for both the model and the error, and then whether this is significantly different than 0 in this case. This whole section here will make more sense once we start running hierarchical regression models. But for now, just note that when you only run one model, it's going to tell you that it's the same as these values. So in the next table, we have our ANOVA table telling us how well the model fits the data. So as you can see here, our model explains a lot more variance than it does not. So we explain more than we have error. So we have a perfectly good ratio here, and it is significant. So we can conclude that our model does fit the data well, and that there is a linear relationship between these 3 quizzes and their final grades. So in the next section, we have our regression coefficients. So you'll notice that it looks exactly like the regression tables or the result tables from simple regression, except that we've added all the additional predictors. So the constant still appears at the top here, and then we have the estimates for each of the other variables. So we have, and then here we have a t-test telling us whether or not that one is significantly linear, in the sense that this value is significantly different than 0, which means that there is a linear relationship between the variables and not a nonlinear relationship. So as we can see here, our 3 quizzes do have a significant linear relationship with final grade. However, our constant does not, but if you recall, that just means where the, or what the value of y will be when all of these are equal 0. So it doesn't matter if this is significant or not. So if you wanted to build your regression equation, you would take these as your slopes for each of your predictor variables. So this would be the slope of quiz 1, this is the slope of quiz 2, and the slope of quiz 3, and then the coefficient is right there. Okay, and sorry, or the intercept rather. The coefficient for the intercept is right there. So we also have here the standardized coefficients. So what this is basically this, but in z-scores. And this is what permits us to compare the relative influence of the different independent variables. Because this section here, if you recall, is going to be in units of the variables that we're examining. And so what this does is allows us to compare it across units of measurement. So in our case here, even though we have the same unit of measurement, because of the variance within individual predictors, we see here that even though it looks like this one has a bigger influence because there's a bigger, or sorry, this one here has a bigger influence because there's a bigger value, it is in fact quiz 2 that accounts for more variance in final grade than quiz 1. And we can see that here by the larger value. And then if we go down here, we do have the bootstrapped confidence intervals for the non-standardized B, so the slope, and we have them right there. Okay, so and then you can just actually ignore this last table. So that's everything you need here. So that was a forced entry regression, multiple regression, where all of the variables were entered into the model at the same time. So now I'll quickly show you how to do a hierarchical one, where we're going to suggest that one should be accounted for first, and then we'll see after that one if the other one still contributes significantly to the model. So again, analyze, regression, linear. So this time, let's say that we want to know if quiz 1, or let's say for whatever reason we know that quiz 1 has already been shown to relate to final grade, but we don't know about quiz 2 and 3. So what we would do is we would remove quiz 2 and 3, and notice here we have block 1 of 1. Okay, so we're in block 1. If we click next, we still have the same dependent variable, but now we're looking at block 2 of 2. So in this case, we will re-enter these back into the model, and we can leave everything else the same. Okay, so all the stuff we just did is all the same, and we still leave this on enter here. So essentially it does 2 rounds of forced entry, but since we're doing 2 rounds, we call this hierarchical. So what it's going to do is first test the relationship between quiz 1 and final grades. So since there's only one variable in that model, it's almost like running, it is exactly like running a simple regression, and then we'll see if quiz 2 and 3 add any value. So we click OK, and again, running the bootstrap analyses. Excellent. Okay, so this time you can see that we ran 2 models. In the first model, we ran quiz 1, where the dependent variable was final grade, and then in quiz 2, we added these. Okay, so we have this combination here. So what we have now are results separated by both models. So we get separate values for everything. So if we start up at the top, we can see that our our correlation coefficient between just quiz 1 and the outcome is 0.89. However, once we add the other ones back in, we get 0.97. And then we notice the R-square goes from 0.8 to 0.97. And again, like last time, the adjusted R-square stays about the same. So it does mean that we have a pretty good model. But here's where the R-square change starts to get interesting. So what this represents is, so this of course is the difference between, since it's the first model, 0 and what we obtained. However, since we ran a second model, it's now comparing what we ran in the first one with the second one. So the difference between the R-square here is 0.796 and 0.972 is actually equal to 0.175. And then if we compare the F statistics, so the ratio down here, we started at 0.87, and then by adding the other predictors in, we jumped up to 50, or 500 and sorry, I said 0.87, I meant to say 187, and we jumped up to well over 500. So what it's running here is a significant test on whether this is significantly different than that. And in this case, we can say that it is. So we can conclude that our second model is actually a better model than the first. If this was not significant, so if it was bigger than 0.05, we would have to say that the first model is better. But in this case, it looks like both models are good, and the second one is actually better because of this. So now we can look at our coefficients, but since we already know that this model is better, we don't really need to look at quiz 1. And as you can see, once you add the other variables in, the relationship between quiz 1 and quiz 2 changes. Sorry, quiz 1 and final grades changes because we now have other variables that are accounting for some of this variance. But as you can see here, in both model 1 and 2, all the quizzes have a significant relationship with final grade. And so you can see that there. And then here we have the standardized versions and the non-standardized versions. And again, since we're using the same data, it's not surprising here to see that quiz 2 still accounts for the most variance out of quiz 1 and 2 and 3, even though here the values are not quite that. So when you look at standardized, you can see which one accounts for the most. And then we get down here and we have our bootstrapped confidence intervals again for both, but since we've already decided the second model is better, we don't need to really look at the first one. So this is the same as the other one. And then finally, an extra table that we get when we run a hierarchical model is that it gives us a list of the variables that have been excluded between the different analyses. So when we ran model 1, we excluded quiz 2 and 3. So we're just getting a table here telling us that. And then again, you can ignore this. Okay, so that's how you run multiple regression in SPSS. Thank you.